let's think about these two species. We've got chromium. Okay. Now, is it clear why we would call these isomers? Well, isomers are species that have the same formula but are different in some way. Well, these are species that have the same formula but they're different in some way. Or isomers are things that have the same elements in the same numbers, but they still differ in some way. Well, these both have the same elements. For example, this has one sulfate and this has one sulfate. This has one bromine and this has one bromine. The same elements, but there seems to be some difference. All right. Now, these are what are called coordination isomers. And that makes sense because in this case, it's the sulfate that's coordinated to the chromine with that coordinate covalent bond, whereas the bromine would be making a purely ionic bond. So here, this would be coordinated, whereas in this case, we're modeling the bromine as being forming the coordinate covalent bond, and this is the ionic. So this would be called coordination isomers because they're identical except for which are the species that are coordinated to the transition metal.
Sorry, the ammonia, should that have a 5 next to it?
Thank you. I said they were identical, but they're not identical without that. That's right. That's an important point. So they have to have not just the same elements, but the same numbers of elements. So it's good that you pointed that out. So now these have the same numbers of elements. So they really are isomers. Without that, they wouldn't even be isomers. They'd just be different compounds. Okay, now these are coordination isomers. All right. I didn't actually see any problems about that particular name, but it's pretty simple if you need that. That's coordination isomers. Now we want the more complicated types of isomers. Well, I did see one question about linkage isomers. Yes. So we can take a look at that. So let's see what are the examples they gave here. Well, there are certain ligands that can connect at more than one atom. So for example, they gave the example of thiocyanate. This is thiocyanate. Well, it turns out that the thiocyanate could be bonded to the transition metal either from the nitrogen or from the sulfur. So it could be the sulfur that's donating the electrons to form the covalent bond, or it could be the nitrogen. Of course, both of these have lone pairs to donate. So either of these could be donating the electrons. Well, if you have two molecules that only differ in whether it's the sulfur or the nitrogen that's donating the electrons, those are linkage isomers. I think that makes sense because they only differ in exactly which atom is linked to the transition metal. And the other example they gave, and I saw this in the homework, was NO2-, which is a nitrite anion. Well, it seems most natural to think of the nitrogen as being connected, but sometimes it's the oxygen that's connected to the transition metal. And when that's the case, they write it like this. So let's consider these two compounds. Are these isomers? Are these two compounds isomers? Yes, because they have the same elements in the same numbers. For example, ammonia, 4 ammonias here and 4 ammonias here. 2 oxygens here and 2 oxygens here. So they are isomers. What type of isomerism do these demonstrate? Yes. All right, surprise, these are linkage isomers. Not coordination isomers like we had up here. Because coordination would be if there were different species inside and outside of the brackets. But here in both cases, we have 1 chlorine in and 1 chlorine out of the bracket. So they're not coordination isomers. The difference here, well, who's connected to the cobalt in this case? Which element is connected to the cobalt here? The nitrogen's connected, but in this case, who's connected?
Oxygen.
Yeah, so this one would be So in this case, it would be the nitrogen that's connected to the cobalt, where here it would be one of the oxygens that's connected to the cobalt. And of course, the cobalt is also connected to 4 ammonias as well in both cases. All right, so this is what's called a linkage isomer. So it's just a matter of learning what this term means. And it's a reasonable name because it talks about having different elements in the same type of, same type of species that are coordinated to the central element. Okay, so that's linkage isomerism. That's relatively straightforward. All right, by the way, for nomenclature, if you're doing nomenclature, this would be called nitro, and this would be called nitrito. All right, so they got that in the book. All right, these are part of a group that are called structural isomers. One thing that's confusing about isomerism is that there's main categories and then subcategories. Well, the two main categories you guys are going over are so different types of isomers. Well, we've got structural isomers, and we have stereoisomers. Those are the two main categories. Structural isomers differ on the basis of who is bonded to whom. They have different connectivity. The connectivity is just who is bonded to whom. Well, these have different connectivity. For example, in this isomer, the cobalt is bonded to the nitrogen, whereas in this isomer, the cobalt is bonded to the oxygen. So they have different connectivity. So both linkage, both coordination, and linkage isomers, those are both types of structural isomer because they both differ based on who's connected to whom. Those are the simple ones. Now we have to deal with the hard ones, which are the stereoisomers. Now the first thing you might wonder is, if things have the same connectivity, how could they be different? But it turns out that things can have the same connectivity and still be different from each other. These are supposed to be 6-membered rings with some chlorines on them, just as a brief example. Now, are these isomers?
Yes.
Yeah, because they've got the same numbers of elements. So they are isomers, but they're not the same thing. Now, do they have the same connectivity? They do have the same connectivity. For example, this chlorine is connected to a carbon, and this chlorine is also connected to a carbon. And also, there are no carbons in between these two carbons. So they have the same connectivity. But they're still not the same because they have different arrangements in space. For example, in this case, the two chlorines are both pointing above the ring. Whereas in this case, one chlorine is pointing above the ring, and one chlorine is pointing below the ring. So stereoisomers are when you have the same connectivity, but different arrangements in space. I think stereo is Greek or Latin for something that has to do with space. These are space isomers. Different arrangements in space. Okay, so these would be what are called stereoisomers. And in fact, would this be cis or trans? Cis, because cis means same side. Well, here the chlorides are on the same side of the ring, and here they're on opposite sides. So this would be trans. Trans means opposite. Just like what transatlantic means for going from between opposite sides of the Atlantic. So trans means opposite, and cis turns out to be mean the same side.